Welcome back. In this video, we began to learn the core part of this course. We will learn what neural networks are and some classification neural networks, activation functions, regularizations, optimizers, and applications. Now, let's see the first part, definition and development of neural network.
Currently, the definition of neural network is not determined yet, and the neural network research in the US thinks and a computing system make up a number of simple and the hardly interconnect the processing elements that will represent the information by the dynamic states represent the external input. Based on the original features and interpretations of neural network, it can be simply defined as an information processing system. It is designed to simulate human brain structure and functions. So we can define artificial neural networks like that. It is the network composed of the artificial neurons, and it attracts and simplifies the human brains based on the microscope structure and functions. This is an important way to simulate human intelligence and reflects some basic features of human brain functions. And deep learning generally involves deep neural networks, where the depth and refers to the number of the layers of neural network in the design and application of the artificial neural network. The basic idea is to simulate the artificial neural networks with one neuron connect to the next neuron, and so simulate that we built the perceptron, and because we just have the one layers, and this layer maybe is the neurons, is the our neurons, and of course is the functions as the neuron. And so we simulate like that, and this is a simple neural network perception. Because it can't solve the XOR problems, we will add many layers and many functions, many formulas in the middle. So the hidden layers have the many layers, and then we will build the deep neural networks like that. So that's called the deep. It's in the middle because they had many layers, and each node have the many functions, active functions. Let's see more details of deep learning development. So building neural network maybe in the 1948 to the 1969. Earlier in 1958, Frank Roosevelt invented the perceptron and the Extrema. The Extrema doesn't solve the XOR problems, so the Marvin Minsky and the Primate Artificial Intelligence questioned that the XOR problems, and the research on the perceptron was doomed to the failure. And from 1986 to 1998, it's developing neural networks. The second generation neural networks with the Hating, and Hating integrate deeper learning expector, and the developed BP algorithm suitable for the multi-layer perception, and use a symbol for the non-linear mappings that can solve the problems of non-linear classification and learning. In 2012, a major top image recognition Connect, Hating's team won the title using the convolutional neural network that boost deep learning development. Also, in 2016, AlphaGo is the Google's AI program based on the deep learning. Defeat Lisando, and this news further promoted deep learning's development. As we all know, the sample neural networks is perception. Let's see more details on it. And it's a perception, and we can see it. It has the input layers, and input layer is our data. It's a vector. Have the weight, and there is the weight, and W0 is the bias, and the activity functions we use the Sigmoid function, and when the natural is larger than 0, it will be the result will be 1. If otherwise, the result will be -1. And it performs biased classification on input samples in the high decimal space in the perception signal and decide the result. And how to get the result, how to get the weight. When we update our weights, we will use the training rules and use the current weights to calculate the perception, the output, and first update each weight as a formulas like that. And the T is the target values, and the O is our output, and eta is the learning rate, the xi and wi as the ith element of the vector and w and weight. When the training sample is linear split, the Presley method is repeatedly used. After finding the times of training, the perception converges to the classifier that can correctly classify all training samples. When the training sample is not linear separated, the training may be unable to converge. Therefore, another rule is designed to overcome this deficiency, namely the data roast, and it used the gradient descent method to search for the possible weight vectors in hypothesis space to find the weight vectors that best fit the training examples. The idea of the gradient descent runs through the whole neural network series, such as the fully connected networks. Together with BP algorithms, it is the cornerstone of the neural network's training theory, and we should master this. The next part, we will start to learn the gradient descent. For the multi-variables, the functions and output will be the f functions, and its gradient at s bar is like that. This we calculate these functions, and the direction of gradient vector is the speediest against the direction of the function. Therefore, the negative gradient vectors and point to the steepest descent decreases of this function. When training samples are not linear spread, we can't find the hyperplane to enable the perception to practically classify training samples. However, we can classify them approximately and allowing some minor classification error. To minimize the errors, we need to first parameterize the error using the loss function. And this loss function has the following features, and this we can use the weight factor as the independent variables, and use the sum of square of the directions between the target output and the actual output of the training examples as the subject. There is a coefficient 1 second. We see that once the training sample is given, its input and the target output values are constant, and the actual output changed with the weight. So the independent variables of the errors functions is the W, and the coefficient 1 second is difficult to understand. When dividing the E with respect to the independent values, and the coefficient and 1 second offset to the coefficient to 1, which will be seen later, and the functions reflect the error between the target output and the actual output of the perception. the independent variable of loss functions, the W, and is the width. So the function is defined as the width space. Then we need to search for a width vector W to minimize these functions. And unfortunately, the formula defines a very complex high decimal curve service like that. It has the high decimals. So there's no effective mathematical method to calculate the Extrema of the high dimensional curve service. We know that the negative gradient decreasing is a distinct direction. So we can start from the point and to go along with the negative directions of this speeded distinct direction, and this is to find the minimum point of the EW, and this is the minimums, and this is the core ideas of the gradient descent method. Let's see the first method after the group both gradient descent algorithms for linear units. Initialize each weight and WIs to random value with a small absolute value, and then before the terminating conditions match, we do initialize each data with data WI to 0, and then for each samples we should do the int the x in the unit and calculate the output. Then we will use the output to calculate the WI, delta WI, and for each WI, and we do update the weight. So the coverage of the process is very slow, but because all training samples needs to be calculated every time when the weight is updated. If the error surface have the multi-local minimums, and the process is easily to trapped into the local extrema. So let's see another method to update data is higher efficiency, and SGD, this algorithms, and this algorithms is one limitations is called online learning, and which updates the gradient based on the each samples. This gradient descent goes to another extrema that is updating the weights for each samples, and because the training samples usually contains the noisy, when approaching the extrema, the gradient is difficult to converge to the extremas. They are produced of the online gradient descent. Let's see from some details. First, we should initialize each WI to the random values, not 0, and with small absolute values. And before the termination conditions match, we should do that. And first, we should enter the unit and calculate the output, and then we should do to enter the W and calculate the WIs, and then we will to opt out the date, and like that. To address the defects of the previous two gradient descent algorithms, another algorithm's mini-bench gradient descent has been proposed. It is the most widely used one, and the idea is use two samples to fix the bench size and to calculate the data WIs and update the weight. And the procedure it is like that. If the first we should initialize each data WI to 0, and then select samples from the whole samples, and for each samples along the sample we should do first we calculate the output, and then to calculate the data WI, and then we should update the WI like that. If there is a last bunch, then describe the training samples sequences. And the gradient descent algorithms consider both efficiency and gradient stabilities. It's easier to oversort local minimums and is the most commonly used gradient descent in our programs and in our daily works. Let's see the important component activation functions. The Sigmoid function is the modest and continuous and easier to devise. The output is the boundaries and the network is very easier to convert. So we can see that it is values from 0 to 1. It's the first functions we used, and touch functions, and this the softmax function, and the ReLU function. ReLU function is we use it very frequently. In most projects, we will find the ReLU functions because when our input values is smaller than 0, and the value will be 0. And if it's larger than 0, and it will be equal to itself. And in other words, it makes the values more equal to 0. That will easier to calculate our functions and to make the process of training our models more faster. For its disadvantage, there's no upper bound, and training is relatively easier to diverge. Also, it's not differentiable at 0 and forcible defined derivative, and it's not smooth enough in some regression problems. Compared with ReLU function, this function has more complex computation. However, it has a continual derivative and define a smooth covered surface. We will define a function which factors to the weakened side. We should consider non-linear. When with activation functions and non-linear, a two-layer neural network can be provided to the common functions approximations. If the function is a linear, the entire neural network is equivalent to a single layer linear models. And continuous differentiable, and this attribute is described for involving gradient-based optimization problems. If some functions that are not locally non-differentiable are selected, the derivative must be defined forcibly. Also, we should consider the range. And when the range of that function is finite, the gradient-based training method tends to be more stable. When the range is infinite, the training gradually more efficient, but it's easier to diverge. Smaller training rates are the typically necessary. Also, the activation is monotonicity, and the loss functions associated with the single layers model is the convex. Smooth function with the monotonic derivative has been the protest generalized be better in some cases, and approximating identity near the orange. When the activity functions have this property, the neural network will learn efficiently when its weights are initialized with small random values. When the activation function does not approximate additive near the orange, special care must be used when the initializing the weights. The activation functions are used for neural networks. Let's see what types of neural networks.
Okay, now we have learned what neural networks are and the traditional models perceptron and training those, and the types of the activation functions. In next video, we will introduce the types of neural networks and some important components of neural networks. Well, thank you for your watching. Bye.